So for this problem, we're told to count the number of prime numbers less than a non-negative number n. So basically what this means is if they give us n is equal to 10, we have to count the number of prime numbers that exist from 2 to 10, because as we know, 1 and 0 are not prime. So the first method that we're going to use is called brute force. It's also known as trial division. So for example, if we were given the integer n is equal to 15, then what this method says is for each number between 2 and 15, we attempt to divide all of the numbers into that number. So for example, let's say that we're going through this process and let's just choose a random number between 2 and n, and let's say that this number is 10. So from 2 to 10 minus 1, which is 9, we're going to attempt to divide each of these numbers into 10. We already know that 2 divides into 10, but for the sake of argument, let's keep going through these numbers so we can see how the process works. We will establish a loop which will go through each of these numbers and try to divide them evenly into 10. So we know that 2 divides, 3 does not, 4 does not, 5 does, 6 does not, 7 does not, 8 does not, and 9 does not. Since 2 divides evenly into 10, we know that 10 is not prime because it breaks the rule of prime numbers, which is that the only divisors that they may have is 1 and themselves. The same process would repeat for the next number. So for example, since we started off with 10, we're going to move to 11. We will check each number until 11 and see if it can divide evenly into 11. We can quickly see that these numbers cannot divide into 11. None of these numbers can. Therefore, if we get to the end and we found no even divisors, then we know that this number is prime, and we can increment our count by 1. While I've only drawn out 10 and 11, remember that this entire process will happen for numbers 2 through 15. You can quickly see that this requires a lot of computation, and it's not a very efficient algorithm. This brings us to the second method of solving this problem, which is using something called the sieve of Eratosthenes. This is an ancient algorithm that was developed a long time ago. It's pretty ingenious how it works. So in order to visualize this correctly, we will again pick a number for n. Let's say that we're given n is equal to 21 as the input. So the first thing I'll do to visualize this is draw out a grid of numbers 2 to 21. And as previously mentioned, we don't include 1 and 0 because these numbers are not prime. So it wouldn't be beneficial to us to spend time on those numbers. So the first step of the algorithm is to go through and add all the numbers that are not crossed out to the list of primes. So obviously no numbers are crossed out right now, which is why we need to start crossing them out. So the first number is 2, which is not crossed out. So what we want to do is add that to our list of primes, and then go through and cross out all of the multiples of 2. From there, we repeat that same process. So since 3 is not crossed out, we will add that to our group of primes. And then cross out all the multiples that aren't crossed out yet. And this process will repeat again for 5. The next number is 7, which isn't crossed out, and 13, 17, and 21. As you can see, if we count all of these numbers up, we have 8 prime numbers in total. This is an example implementation of this algorithm. As you can see first, if n is less than or equal to 2, we can return 0, because 1 and 0 are not prime. We can then see that we initialize a variable called count, which is equal to 0, and a Boolean array, in this case a vector, that is equal to the size of n. In this loop, we start I equal to 2, and we only have to check up into the square root of the in or the input provided. And the reason for this is that no multiples that haven't been crossed out already exist above the square root of n, so we can stop there. If v at index I has not been crossed out, or if it's false, we start our inner loop at the first multiple by squaring I and then adding on I at every iteration to keep getting the multiples of I, and we set each of these values equal to true, which is just crossing them out in this program. Once we're finished, we go through the entire Boolean array and check if any are not crossed out. If so, we increment our count and return that number at the end.